May I start my presentation?
Yes.
Okay. The title of my report is Multilayered Inhomogeneous Viscoelastic Rod Moving in Vertical Direction, a Delamination Analysis. The rapid development in the field of multilayered inhomogeneous structural materials contributes for widening of their application in various sectors of modern engineering. The excellent properties of these materials make them an attractive alternative to traditional materials like metals and alloys in different engineering structures, mechanisms, and devices. This paper is focused on the lamination analysis of a multilayered inhomogeneous rod moving vertically upwards. The rod acceleration is known, therefore the inertia loading acting on the moving rod can be determined by applying the principle of D'Alembert. The inertial loading is distributed non-uniformly as a result of material inhomogeneity. The rod under the inertial loading has nonlinear viscoelastic behavior that is treated by a model structured by nonlinear and also linear springs and dashpots. The rod is made by concentric layers having different material properties and thickness. There is a delamination crack between layers. The crack represents a circular cylindrical surface. The complementary strain energy in the rod is determined and used to obtain the strain energy release rate.
Excuse me, can you hear me?
Yes, I now hear you.
We cannot see your slides.
Okay, one moment. This is the first figure.
Okay.
Okay. This paper is focused on the lamination analysis of the multilayered inhomogeneous nonlinear elastic rod moving vertically upwards. And this rod is shown in figure 1 on your screen. The rod acceleration is known. The radius of the rod cross-section is R1. The rod layers are concentric. They are inhomogeneous in both thickness and length directions. The variation of the bulk density of the material along the thickness of the layer is given in equation number 1. In this equation, R is the radius, rho alpha I is the bulk density of the material at the internal surface of the layer. Beta I is a parameter, N is the number of layers. Equation number 3 describes the variation of rho alpha I along the rod length. Here, X is the centroidal axis. The origin of this axis is in the rod lower end. Rho delta I is the value of rho alpha I in the rod lower end. L is the rod length. Omega I is a parameter. The intensity of the distributed vertical loading Qi acting in an arbitrary point in the rod is given in equation number 5. Here, G is the gravitational acceleration. The first and the second terms in the right-hand side of equation number 5 are the intensities of the loading from the rod's own weight and the inertial loading induced by the rod acceleration. Equations 1, 3, and 5 indicate the Qi varies with buff layer thickness and rod length. The rod nonlinear viscoelastic behavior is treated by a model structured by linear as well as nonlinear springs and dashpots, shown in figure number 2 on your screen. The spring with modulus of elasticity EI and the dashpot with coefficient of viscosity eta I have linear mechanical behavior. The behavior of the dashpot and spring BFI and MPI is nonlinear. The stress sigma I applied on the viscoelastic model is constant. Because the rod is under a loading that does not depend on time, the strain epsilon I in the viscoelastic model is given in equation number 6. Here in this equation, epsilon EI, epsilon BFI, and epsilon MPI are the strains in the linear spring, the nonlinear dashpot, and the nonlinear spring. The constitutive laws of the linear spring and dashpot are given by equations number 7 and 8. In these equations, sigma EI and sigma eta I are the stress in the spring and the dashpot. Epsilon eta I dot is the time derivative of the stress in the dashpot. The stress-strain time relationship for the linear spring and dashpot under the stress is given by equation number 9. Here, T is the time. Equations number 10 and 11 define the constitutive laws of the nonlinear dashpot and spring in the viscoelastic model. In these equations, sigma BFI and sigma MPI are the stress in the dashpot and the spring. Eta BFI, mu I, ni I, di, li, and hi are material parameters. The stress in the nonlinear dashpot and spring are equal to stress sigma I applied on the model. From equations number 10 and number 11, after some transformations, we obtain equation number 14. This equation leads to equation number 15. Then, using equations number 11 and 13, we find the relation that is given in equation number 16. Equations number 6, 9, 15, and 16 led to stress-strain time relationship given in equation number 17. The stress-strain time relationship in equation number 17 is applied to treat the nonlinear viscoelastic behavior of the rod layers. The variation of material parameters along the thickness of the rod layer is given in equations from number 19 to number 22. In these equations, E alpha I, eta BF alpha I, and D alpha I are the values of the parameters at the internal surface of the layer. Beta EI, beta eta I, beta N BFI, and beta DI are parameters. Equations from number 24 to number 27 describe the variation of E alpha I, eta alpha I, eta BF alpha I, and D alpha I along the rod length. In these equations participate different values of these parameters in the rod lower end. As already stated, there is a delamination crack between the layers of the moving rod. The crack is a circular cylindrical surface with radius R2 and is located in part B1, B2 of the rod. The crack front is in section B2 of the rod. The delamination crack length is A. The strain energy release rate in the rod is found by using equation number 29. In this equation, at N1 is the number of layers in the internal arm of the crack. U0I asterisk, U0VI asterisk, and U0UI asterisk are the specific complementary strain energies in the cross sections of the layers in the internal and external arms of the crack behind the crack front, and in the cross sections of the rod layers ahead of the crack front. The specific complementary strain energy in the cross section of the layer in the internal arm of the crack is given in equation number 30. The strain epsilon I is found from the equilibrium condition given in equation number 31. Here N is the axial force in the internal crack arm. Equation 32 is applied to derive this axial force. In equation number 32, Vi is the volume of the layer in the internal arm of the crack. The specific complementary strain energies are extracted from the stresses and strains in the cross sections of the layers of the external crack arm behind the crack front and in the cross sections of the layers of the rod ahead of the crack front by applying formulas analogical to that in equation number 30. The strains are determined from equations which are analogical to equation number 31. The axial force in the cross section of the external crack arm behind the crack front is found by integrating of the distributed loading in the volume of the layers of this crack arm. The axial force in the rod cross section ahead of the crack front is found by summing the axial forces in the two crack arms. The strain energy release rate solution determined is checked by an approach according to which the strain energy release rate is the derivative of the rod complementary strain energy with respect to the delamination crack area. This approach leads to strain energy release rate, which matches the strain energy release rate found by the solution derived in this paper. The dependency of the strain energy release rate on the rod acceleration is investigated here. The relations between the strain energy release rate and various parameters of the theoretical model are studied too. These relations are presented in form of different graphs. For example, the relation between the strain energy release rate and parameter beta 1 is plotted in figure number 3 at 3 magnitudes of the rod acceleration. In figure 3, we can see that both beta 1 and W have significant impact on the strain energy release rate, resulting in an increase in the delta. This means that the increase in the bulk density of the material along the thickness of layer 1 and the rod acceleration result in an increase in strain energy release rate. In figure 4, we can see how strain energy release rate is related to the parameter beta E1 when the parameter beta eta 1 changes its volume between 0.5 and 2.0. Growth of beta E1 and beta eta 1 results in a reduction of the strain energy release rate. This indicates that growth of volumes of E1 and eta 1 across the thickness of layer 1 leads to a reduction of the strain energy release rate. A relation between the strain energy release rate and parameters omega eta bf1 and omega d1 is also analyzed. This relation is illustrated by the graphs shown in figure number 5. Reduction in the strain energy release rate resulting from increasing the volumes of omega eta bf1 and omega d1, which can be seen in figure number 5, means that increasing of the volumes of these parameters across the thickness of layer 1 leads to an improvement in the delamination behavior of the moving rod. In conclusion, it can be recapitulated that the analysis reported in this paper can be applied in fracture mechanics based design of moving rods, multi-layered rods with material inhomogeneity and rods that exhibit nonlinear viscoelastic behavior. This is my presentation. Thank you very much for your attention. If you have questions, I will try to answer.